The wing design flaw that made B-17s nearly indestructible. American bomber crews called it bringing the boys home alive. While sleek B-24 Liberators crumbled under German cannon fire, B-17s returned to base with holes you could walk through, wings Swiss cheese by flak, engines shot out, tail sections nearly severed. What's more, the secret lay in Boeing's controversial thick wing design that aviation experts initially mocked as aerodynamically primitive. Remarkably, this 6-meter wing chord created internal voids where enemy shells passed harmlessly through, missing critical structures that kept other bombers airborne. And here we are, in February 1943, somewhere over the Reich. Lieutenant Robert Morgan gripped the controls of his B-17 as flak tore through the fuselage like angry hornets. But something impossible was happening. Holes the size of dinner plates punched clean through the wing, yet Memphis Belle kept flying. What kept this aircraft airborne defied everything aerodynamics textbooks taught about wing design. By this point, when normal designs weren't working anymore, anything became fair game. By 1934, European skies had become graveyards for bombers with conventional thin wings. Furthermore, the Spanish Civil War proved one terrifying fact. Existing aircraft simply couldn't survive concentrated fighter attacks in dense flak fields that would define the coming war. Consequently, Boeing's engineering team faced an impossible choice. Military doctrine demanded strategic bombers capable of precision attacks from 25,000 feet, but every prototype with standard wing designs crumbled under simulated combat conditions. Then chief designer Claire Egtvedt made a decision that would horrify aerodynamicists but save thousands of air crews. He threw out 60 years of speed-first wing philosophy. The unforgiving reality became undeniable. Thin-wing bombers suffered catastrophic failure rates approaching 90% crew casualties over defended European targets. Moreover, German Me-109s and FW-190s exploited a fundamental weakness. Conventional aircraft wings contain fuel lines, control cables, and structural spars in compact spaces where a single 20mm cannon shell could sever everything simultaneously. Subsequently, test data from 1935 revealed the mathematical brutality of aerial combat. Standard bomber wings, optimized for minimum drag, created what engineers grimly called single point of failure zones. As a result, one cannon burst through a thin wing section could rupture fuel tanks, sever control cables, and shatter primary spars, turning a 30-ton bomber into falling debris within seconds. However, Boeing's wind tunnel experiments uncovered something extraordinary. Their thick wing Model 299 prototype absorbed identical damage patterns while maintaining structural integrity. Specifically, the secret lay not in what the wing contained, but in what it didn't contain. Vast internal voids that allowed projectiles to pass through without hitting critical systems. But just as breakthrough seemed possible, administrative reality intervened with devastating precision. Unfortunately, the War Department's procurement committee, obsessed with speed specifications, viewed Boeing's thick wing proposal as aerodynamic heresy. Meanwhile, Consolidated Aircraft's sleek B-24 Liberator promised 310 miles per hour maximum speed, nearly 40 miles per hour faster than Boeing's lumbering Fortress concept. Furthermore, internal Boeing memos from 1936 revealed the company's desperation. Executive Claude Shannon wrote to company president Philip Johnson, "The military wants a racehorse, but we're offering them a Sherman tank with wings. Unless we can demonstrate unprecedented survivability advantages, the program dies in committee." Additionally, the engineering establishment ridiculed Boeing's approach mercilessly. Lockheed's chief aerodynamicist, Kelly Johnson, publicly dismissed the thick wing concept as a flying barn door that violates every principle of efficient flight. Yet unknown to critics, Boeing's one-tunnel data showed something that would change aerial warfare forever. Their slow and heavy design could return home with damage that would destroy any contemporary bomber. The military specifications seemed designed by sadists: carry 4,000 pounds of bombs to targets 1,000 miles away, maintain formation precision at 25,000 feet, and survive concentrated interceptor attacks that no existing aircraft could endure. As a result, standard aerodynamic theory declared this combination physically impossible. You could have speed, payload, or survivability, but never all three. Boeing's solution defied 6 decades of wing design orthodoxy. Instead of the razor-thin Davis airfoil dominating contemporary aircraft, they selected the thick, blunt Clark Y profile, a design most engineers considered obsolete. Consequently, the Clark Y's 11.7% thickness to chord ratio created massive internal volume, but generated drag coefficients that made aerodynamicists weep. When the calculations were complete, Boeing's wing route measured an unprecedented 6 meters from leading edge to trailing edge. Competitors gasped at the dimensions. This wing was nearly twice as thick as anything flying in 1935. However, what shocked the engineering world was the discovery hiding inside this aerodynamic monstrosity. By this time, two philosophical approaches dominated American bomber development, and they couldn't have been more different. On one hand, consolidated aircraft pursued evolutionary perfection. Their Davis wing achieved remarkable efficiency through mathematical optimization, minimal frontal area, and streamlined fuel storage. Clearly, the B-24 represented the pinnacle of speed-first engineering. In contrast, Boeing chose revolution over evolution, accepting horrific aerodynamic penalties for unknown combat advantages. Wind tunnel data revealed the brutal trade-off. The B-17's thick wing generated 23% more drag than comparable thin-wing designs, limiting maximum speed to 287 miles per hour versus the B-24's impressive 310 miles per hour performance. Nevertheless, Boeing's structural philosophy contained a hidden genius that wouldn't become apparent until combat operations began. While the B-24's thin wing packed critical systems into minimal space for maximum efficiency, the B-17's massive wing volume allowed unprecedented system separation and structural redundancy, design characteristics that seemed wasteful until German cannon shells started flying. What the engineers ultimately achieved was unprecedented. They had somehow managed to combine massive internal volume, structural integrity, and self-sealing capability into a single wing design that military theory claimed was impossible. Moreover, the breakthrough came through revolutionary duralumin spar engineering. Two massive main spars created an internal framework strong enough to support the aircraft even with extensive battle damage. Furthermore, the wing's internal architecture resembled a honeycomb more than traditional aircraft construction. Specifically, self-sealing fuel tanks occupied protected positions between structural ribs, while control cables ran through separate channels that couldn't be severed by single projectiles. As a result, this distributed system approach meant multiple hits were required to disable critical aircraft functions. Most remarkably, Boeing's most radical innovation involved deliberate structural gaps, spaces designed to allow enemy projectiles to pass through without striking vital components. Consequently, German pilots would soon discover the frustrating reality of pumping cannon shells into a B-17 wing, only to watch their target continue flying with holes you could crawl through. October 30th, 1935, Boeing test pilot Leslie Tower climbed into the Model 299 prototype for what should have been a routine demonstration flight. However, at exactly 110 feet altitude, something went catastrophically wrong. The control surfaces locked, the prototype stalled, and Tower had less than 5 seconds to solve an impossible problem before the aircraft slammed into the ground, killing Tower and Army pilot Major Ployer Hill. Subsequently, the crash investigation revealed a tragic irony. The revolutionary wing design performed flawlessly, but a forgotten gust lock had prevented the control surfaces from responding. Despite this success, Boeing's thick wing concept had survived its greatest test. A bureaucratic protocol nearly killed the entire program. As a result, military evaluators questioned whether such a complex aircraft could ever be safely operated by combat crews. Meanwhile, wing loading stress tests pushed the B-17 prototype to its structural limits under simulated combat conditions. Engineers applied loads equivalent to 7.5 Gs, while technicians fired .50 caliber bullets through the wing structure. Although the massive spars absorbed punishment that would have shattered conventional wings, early test flights revealed unexpected handling characteristics that defied engineering predictions. When the test data came back from the first high-altitude trials, even Boeing's engineers couldn't believe the numbers. Service ceiling of 31,000 feet, performance that exceeded every contemporary heavy bomber by nearly 6,000 feet. Surprisingly, the thick wing that critics dismissed as aerodynamically primitive was generating unprecedented high-altitude performance through sheer internal volume and structural integrity. Additionally, formation flying tests revealed another shocking advantage. While sleek competitors like the B-24 required constant throttle adjustments to maintain position, the B-17's massive wing provided inherent stability that made tight formation flying almost effortless. In fact, test pilots reported that the aircraft practically flew itself in formation, a characteristic that would prove invaluable during combat operations requiring precision bomb runs. However, the most startling discovery came during damage simulation tests. Technicians systematically destroyed wing sections with explosives, cannon shells, and structural saws, yet the B-17 continued flying with damage that would have been fatal to any thin-wing aircraft. Remarkably, one test flight returned to base with 18 square feet of wing surface completely missing, and the pilot reported normal handling characteristics. Even with revolutionary performance data, the B-17 program teetered on the edge of cancellation throughout 1936. Unfortunately, the Army Air Corps awarded Boeing a token contract for just 13 aircraft, barely enough to keep the production line operating, while competitors like the B-24 received orders for hundreds of units. Furthermore, Boeing's financial gamble on survival-oriented design philosophy pushed the company toward bankruptcy. Manufacturing the complex wing structure required specialized tooling that cost 3 times more than conventional production methods, while the thick wing's intricate internal architecture demanded precision assembly techniques that slowed production to a crawl. Nevertheless, combat reports from Europe were beginning to validate Boeing's contribution controversial approach. RAF Bomber Command's catastrophic losses over Germany, sometimes exceeding 50% on a single mission, demonstrated that speed alone couldn't guarantee survival. Therefore, military planners gradually recognized that Boeing's slow and heavy fortress might be exactly what strategic bombing doctrine required, an aircraft that could absorb tremendous punishment and still complete its mission. Obviously, nobody expected this high-altitude strategic bomber to become the most accurate daylight bombing platform in aviation history. But combat revealed hidden potential that even Boeing hadn't anticipated. Specifically, the massive wing's inherent stability transformed formation bombing from an art into a science. As a result, formation bombing accuracy improved dramatically compared to other heavy bombers. While B-24 crews battled unstable flight characteristics that scattered bomb patterns, B-17 formations delivered devastating precision strikes. Finally, the Norden bomb site found an aircraft stable enough to use its full potential. Consequently, high-altitude precision bombing mission success rates consistently exceeded B-24 performance statistics by margins that shocked Air Force planners. Moreover, B-17 crews reported confidence levels that directly influenced mission effectiveness. They trusted their aircraft to bring them home. Post-war testimony from Luftwaffe pilots proved the grudging respect German fighters developed for the B-17's structural resilience. As one pilot admitted, the B-24 would break up with concentrated fire, but the B-17, that was different. You could shoot holes through it all day. Similarly, German technical intelligence reports from captured B-17 showed methodical analysis of the wing construction methods. Interestingly, Messerschmitt engineers couldn't understand how such thick, seemingly primitive wings could maintain structural integrity under combat conditions that destroyed more advanced designs. Furthermore, Focke-Wulf 190 combat reports documented ammunition expenditure requirements against B-17 targets that horrified German logistics officers. What should have been quick kills became ammunition-draining battles of attrition, with B-17s absorbing damage that would have obliterated other aircraft. The Schweinfurt-Regensburg missions of August and October 1943 demonstrated B-17 wing damage survival statistics that redefined what aircraft could endure and still fly. Specifically, of the 376 B-17s that attacked these heavily defended targets, 60 were lost, but 316 returned home despite damage that should have been fatal. Similarly, Black Thursday, October 14, 1943, revealed comparative loss rates that validated Boeing's design philosophy. While B-24 loss rates approached 30% on similar missions, B-17s consistently showed 15 to 20% lower casualty figures. Clearly, the thick wing was literally saving lives through structural redundancy. Meanwhile, D-Day preparation missions throughout 1944 showcased B-17 operational reliability under sustained combat operations. While other bomber types required extensive maintenance after heavy battle damage, B-17s flew multiple missions with patched wings and jury-rigged repairs that would have grounded any other aircraft. The legendary All-American incident of February 1, 1943, provided dramatic proof of B-17 wing structural integrity when it collided with the German Messerschmitt Bf 109 over Tunisia. Although the enemy fighter sliced completely through the fuselage behind the wing root, the wing structure remained intact enough for pilot Kendrick R. Bragg to execute a miraculous landing. Additionally, combat damage documentation from aircraft like Champagne Lady showed wing sections with over 200 individual holes from flak and fighter attacks, yet structural failure never occurred. In contrast, the thick wing's internal framework absorbed damage that would have caused catastrophic wing failure in thin wing designs. Moreover, crew survival statistics directly correlated with B-17 wing design advantages. The massive wing's fuel tank self-sealing capabilities, combined with structural redundancy, reduced fire-related casualties by 40% compared to other heavy bomber types operating in the same combat zones. Daylight precision bombing doctrine viability depended entirely on the B-17's damage absorption capabilities. Without aircraft that could survive concentrated fighter and flak attacks while maintaining formation integrity, the entire Allied strategic bombing campaign would have collapsed by late 1943. Furthermore, the combined bomber offensive success rates were directly influenced by B-17 crew survival statistics and aircraft return rates. Air Force planners discovered they could sustain bombing campaigns using B-17s that would have been impossible with less durable aircraft. The thick wing literally enabled strategic victory. Ultimately, Allied strategic bombing campaign sustainability was enabled by B-17 operational durability that exceeded every other heavy bomber in service. While the sleeker, faster B-24 required extensive maintenance and suffered higher loss rates, the B-17's robust wing design allowed continuous operations that ground Nazi war production to a halt. By 1943, the numbers told a brutal story. story that would haunt military planners for decades. The B-24 Liberator screamed through European skies at 290 miles per hour, 3 precious miles per hour faster than the B-17's lumbering 287 miles per hour maximum velocity. However, every morning, more Liberator crews failed to return home for breakfast. Additionally, the B-24's sleek Davis wing could stretch missions to 2,850 miles, nearly 850 miles beyond the B-17's operational radius of 2,000 miles. But here's what the engineering reports didn't capture. When flak started bursting and Messerschmitts dove from above, speed meant nothing if your aircraft disintegrated around you. Nevertheless, the survival statistics revealed a more complex truth than Boeing's marketing suggested. While combat conditions varied significantly, B-17 flying fortresses suffered approximately 1.66% loss rate per sortie in 8th Air Force operations, while B-24s experienced 1.26% losses per mission. However, this apparent B-24 advantage came from assignments to shorter, safer missions. When both aircraft faced identical deep penetration targets, the B-17's structural resilience proved its worth through crew testimonials and damage assessment reports that defied statistical simplification.